Density is a characteristic of substances, something we need. Density basically is mass divided by volume. So how much stuff there is in a certain space. Then if we modify this, multiply both sides by volume, we need to be able to do that stuff, not just take this as some kind of like magic, like given or something like that, religious given, multiply by volume. Mass is density times volume. Or if you got mass and density, you can get volume. Volume mass over density. Okay, so multiply both sides by volume. Volume times density is mass. And then get that and divide by density. Mass divided by density is volume. You need to be able to use this formula to get different information from it, since these are related like that. And we need this stuff because we can't always get the mass or the weight of something. We have to do this. Some things, am I going to get the volume and density of this and get the mass? Hell no. We weigh it and get it from there more easily. However, some things we have to. Are we going to see, for the purposes of studying geology and ecology, or civil engineering, or flooding, or swimming in a river, or fishing, or going boating, are we going to get a piece of river and weigh it? Not possible. It's absurd. We have to use this if we're going to know the weight or flow rate and stuff like that. There's some rivers if we're going to study it. Of course, we're not going to know weight for flow rate and stuff, but some stuff, calculations and similar stuff goes on to get that. But from what I'm thinking about in general, not this of course, but to get the weight of some river, you have to estimate the volume, you have to know the density of water, and then you can get the mass. Otherwise, not going to happen. Some things, it's impossible or impractical to get the weight and then the mass. You have to know what the density of a substance is, calculate or estimate the volume, then you can get the mass. So it's essential in thinking. Like some asteroids or things out in space, are we going to weigh them? Ha, not possible, ludicrous. We can figure out with modern physics what it's made of. We can get the density of that stuff. We can calculate the volume of some thing in space, then get the mass, things like that. We can get the mass in other ways too, but this is one thing that's possible. So this is what we need to know for it. So for example, some everyday things too, like the mass or the density of water is 1 gram per cubic centimeter is like standard. And then that's a good thing to remember and then relate from there. Then like looking in this chart, hydrogen gas, because it's a gas, it's less dense, there's less stuff in a certain volume, easier to move through air than water, easier to move through water than ice, you know? But that's a little different. But I should say more easier to move through water than like a chunk of lead or a chunk of iron. So one thing about it is the density as well as the state. But, because, you know, ice is a solid, so density isn't so much of a factor as like the state. But hydrogen, density of 0.0 0.00009 grams per cubic centimeter. So tenth, hundredth, thousandth, 10,000th, 100,000th, 900 thousandths of a gram per cubic centimeter. So way, way, way less than water. So round up to 0.0001. So 1, 2, 3, about 10, 100, 1,000. About, so hydrogen is about a 10,000th of the density of water. And nitrogen, and these are STP, standard temperature and pressure. Nitrogen is about 1,000th of the density of water, liquid, gas, nitrogen. And lithium, a metal, is about 0.5 grams per cubic centimeter, about half as dense as water. And then water at 4 degrees versus 20 degrees. Water at 20 degrees is a little bit less dense than water at 4 degrees. Seawater and milk are a little more dense than water, 1.03 versus 1. Solid coal, that's a little more dense than water, not much. Blood is about 1.6 grams per cubic centimeter. And granite, about 2.6 grams per cubic centimeter. Lead is like 11.3 grams per cubic centimeter. So there's more stuff in a little cubic centimeter than water or blood or whatever. And I'll put this chart up and someone can look at it if they would like. Liquid mercury, uranium, stuff like that. So if we got, for example, lithium, 0.534 grams per cubic centimeter. Let's say we got a sphere of lithium. Let's say a sphere of lithium, radius 2 centimeters. Then the density is 0.534. And we want to know what the mass is. So we do density times volume. For a sphere, the volume is 4/3 pi r cubed. And so 2 to the third is 8. Pi over 3 is about 1, a little more. 8 times 4 is 32. So maybe 34 cubic centimeters. Let's see. Quit. Clear. So 4 divided by 3 times pi times 8. 33.5 cubic centimeters. And then multiply that by the density times 0.534. So 17.9 grams. Okay, so that's what we do to get mass. Because a lot of times we're given the density and we use it to get other things. We use it to get mass, we use it to get volume. Here, use it to get mass. 17.9 grams of lithium. And then we can use that for other things. In physics, now we know the mass, make it kilograms. We could do something with force and then equations of motion. You could put this into chemical reaction and get some information from that. but that's the basic idea. So it characterizes a substance because people might think, why do we have to deal with density? But the volume of stuff always changes. You get a glass of water, you got more water in it or less water, more volume or less volume. You can have different masses of the substance. You can have a little bit of water and it's a certain mass. More is a different mass, different weight, different mass. More pizza on the plate, there's more mass. The more pizza, more tenderloin, more stuff, more mass, you know? Or iron, you got some iron. You can have different volumes of it, different weights, but what's the same? It's, we need to have something the same in all these things because iron is iron, so there should be something the same about it. And one thing, among others, is that the density of iron is the same. You know, like water, it can vary at different temperatures. There's things that affect it, but in certain conditions, obviously, conditions matter. Stuff isn't always true out of no context whatsoever. There has to be context. In a certain context, you're going to have this uniformity, this sameness for every piece of iron or every bit of water. So this is important in helping us deal with all these situations. It goes back to the ancient Greek thing of finding the one in the many. People who find the one in the many are successful. Those who fail, those who don't do it, are confused and aren't as successful. Philosophy matters, ideas matter, not just doing little teeny tiny things. It's this in the big picture, and no one would ever come up with this unless they were looking for the one in the many anyway. It goes back to Thales and some ancient Greeks. Even though Thales was wrong on some things, he was looking for the one unifying thing in everything in the world, everything in the universe. But that idea led to this, and that's why, for example, the one in the many, what do we have? Electricity and magnetism are known to be the different aspects of the same thing now. It's the same underlying phenomena. It's the quest to find the one commonality in the many different things. You have an electric shock and you have a compass, they're so different. Nope, different aspects of the same thing. They are very different, but there is this underlying commonality. You know, what's the same in all things of iron? What's the same in all, like, planets? Figuring out, when Kepler figured out his laws of planetary orbits, he was trying to find the one in the many. What is the same amongst all circles? That's what Newton did. So regardless of all these other different factors going on, we know for circles that the centripetal acceleration is v squared over r, no matter what. No matter what thing we're dealing with, whether it's a bird or something twirled on a string, a bird circling, something twirling on a string, a planet going around, or a moon going around a planet in a circular orbit. That's the one in the many. So notice, if you know this, you're going to be more successful and efficient. Other people will be confused. This is so different than this. I can't do anything with them. Oh my gosh, I'm lost. They don't get philosophy. They don't get good thinking skills. They're confused. They're not going to do well. Get good philosophy, good thinking skills, form concepts. Your thinking is going to be much more efficient, and your ability to do things will be much more powerful. Very important. So this is a good example of a much broader, deeper philosophical idea and this philosophical insight into doing science and thinking. You know, like, what do we do when we summarize a person? What's the essence of them? We got to find, like, the one principle in all the diverse things they do, or in a culture. What is the one or the few ideas that explain most everything else? It's finding the one in the many. Very important. Just like with this. No matter what kind you think, the thing you see on some different tests, or situations, or things in the world, centripetal acceleration is v squared over r. Okay? So this is one little example of finding the one in the many. It helps us characterize things. No matter how much stuff you have, how much clothing made of cotton, or what the mass of it, or the volume, the density of cotton is the density of cotton for the different shirts and whatever, you know. Or no matter what, how much water you're drinking, with the volume, the mass, the density is the density is the density at a certain temperature and all that. So it's important, and then I'll show you some other ways in another video about how we can do a little bit more with this. But some density basics.